Hi, everyone. So this is going to be another one of our continuing tinyML, AutoML tutorials. And today we're going to have a deep dive with Edge Impulse with Louis Moreau. Just before I pass things over to Louis, I just want to thank our strategic partners, who are the people who really make these webinars possible. I'd also like to point out again that there is the tinyML EMEA Innovation Forum, which is happening next week in Cyprus. It's going to be a great event with a lot of different and interesting presentations going on. Also, if you want to get more involved with tinyML, we have a vibrant meetup group, 146 groups in 37 countries. You can get to those on this link here. We also have a good community on LinkedIn where you can subscribe. And also very important is our channel on YouTube, which has all of the recordings of all the past events, and you can subscribe to that. And this video, the video of this session will be on there as well.
So I'm super excited to be here today. This is actually the first time I will speak about the Eon Tuner, which is our AutoML tool, but not only. Usually I give talks about computer vision stuff or, well, many different things. But this AutoML thing, I'm really excited to present it because that's the first time. That being said, my name is Louis Moreau, and I'm a developer relation engineer with Edge Impulse. I've been at Edge Impulse for about a year and a half. When I started, we were only 15 by the time, and now we are, I think, 66 employees or 67. So things are going really fast, and that's incredible. Before that, I started my career connecting rhinos in Africa. So I was an embedded developer, and I developed a small GPS tracker that looks actually like that. That was fun. I was going on the field several times. After that, I did some technical marketing management and also some full stack engineering jobs. And now I'm focusing on embedded machine learning, and I'm teaching things. I'm also a teacher in my spare time. So I'm pretty sure you're all aware of that because you're here part of the tinyML webinar. When we used to do a traditional programming, especially, for example, on accelerometer data, this is things that I've done in the past. When you wanted to program, you had some inputs, then you were defining the rules, and then you had the outcomes. So, for example, on the Rhino example, is a Rhino is moving or not? You need to go through a different threshold, etc. That was super complicated. Then machine learning arrived, and the paradigm shifted a bit, and you have the incoming. Well, you've got your data that comes with labels, and then the model will learn the rule by itself, and then it will define things. Then you will be able to reuse that, so you can put input data and you will get predicted outcomes. So that's really a change. And in embedded machine learning, the reality is that it's not that simple. We need to focus on the edge devices, and the edge devices have several constraints, whether it's the size, the RAM, the ROM. So we need to make sure the model we are going to deploy is actually accurate, so provide accurate information, and is also, well, the model will fit on the device. So we need to go over a loop. So we need to collect some data. We need to design our machine learning model, so including digital signal processing. I'm going to come back in that in a minute. Once we've got our model, we need to test it to make sure it will work, not only on test data, but also on the field. We need to deploy, and then we do that over and over again. When we speak about the design parts, we have several steps usually. So we have the input data that can be, for example, here on voice, they have a length, so window size. Then we need to extract some meaningful features from this raw data to pass that to the neural network, which will then be able to learn and make some predictions. So those steps can be actually pretty complicated. So every single machine learning project starts with data, and I want to make you participate. So this is an example of a project I've been working on. So the goal is to recognize the voice. So it's a keyword spotting model, and we are going to train a model to recognize the word tinyML. So to do that, we'll do that together. So you can flash the QR code, which is just here, and then it will output like a screen or a web page on that. And I will ask you to collect your voice, like saying tinyML for 10 seconds. Make sure to keep a 1 second window in between. For example, tinyML, wait a second, tinyML, etc. So we have a tool that will extract the meaningful words. I'm going to go to the project while you're doing that. I'm actually going to do that once, so you can have a look at what's going on. So I'm going to flash this QR code. Open that, get started. So I'm going to record tinyML for 10 seconds. tinyML, 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 tinyML. Okay, so now automatically the process is gathering the tinyML information. So I can select a couple just to make sure it works properly. tinyML. Okay. tinyML. tinyML. Great. So we have new tinyML keywords. tinyML coming. So here, every single sample have a length of 1 second. So I'm just going to wait another couple of seconds to make sure everyone has some time to actually collect some words. It's cool to use this technique because I can ask as many people as I want, for example, in a company, to record a voice or their own voice. So I will have a data set that is more various. We'll have, for example, if it's a female voice, if it's a kid voice, or etc. I can have some diversity in my data set. So okay, I see that now no new. Oh yeah, I've got some new coming in. So we have at least one parameter here, which is the window length, or the length of the sample. Then if I want, I'm going to just to explain you, I think I haven't been clear about that. I'm going now to show you how to train a neural network, or at least a machine learning model, without the Eon Tuner, just to show you the complexity of it. We have some predefined parameters, but then I will show you that only with 1 click or 2 clicks, you will be able to find the right balance in between the parameters. But first, I want to show you how complicated this can be. So once my data set is almost ready, so I also got some unknown words. That's a word that, another word, and I've got some noise. Sorry for that, maybe not super comfortable. Then once I've got my data set, I can navigate to the Create Impulse tab. And here I've got several things that I can set up to create my machine learning pipeline. First is the window size. The window increase will be how much you will shift in your data set to create more. For example, this does not really apply for keyword spotting projects, but if you want to recognize continuous noise or continuous motion, you will be able, for example, to set a window increase of 333 or something like that. Let me put back 1,000. So I will only take the sample and then take the other data sample and so on. So I'm not going to take a half part of it and then shift it a bit. So that can be a complexity. Some people don't really understand that when they get started. Then we need to extract some meaningful features from the raw data. From there, we use a processing block. We have several options for processing blocks. We have MFCC for using male frequency spectral coefficients, which is actually great for human voice. But by experience, I also noticed that sometimes MFE, which is another audio preprocessing block, works well. So here I'm going to select this one, but I could also select spectrogram. At some point, I can be lost and I don't know really what to do. I'm just going to go with the default parameters. And then I've got also several options. Once the features have been extracted, to train the neural network. Here, I've been using a technique called transfer learning. This is actually another great topic that we could talk about for another webinar, how to apply transfer learning on voice. Usually we do transfer learning on images. But here I've got, again, several options. So either classification, so basically have access to the Keras API and write your neural network. Regression, it's not applicable in our case. We don't want to predict integers or float values. And then transfer learning. So this is the one I've chosen. Again, this is by experience, and it's also because it's proposed by Edge Impulse when you get started. And my outputs will be 3 features or three classes. A prediction in between noise, the word tinyML that we want to recognize, and unknown. I can save my impulse. And then here again, I've got loads of parameters that I can change. For example, the frame stride, if we change that, for example, here you can see it's an estimation of the processing time that will be on the, I can't remember which board I've selected. So Arduino Nano 33 BLE cents, which has a Cortex M4F. So keep in mind that this is 332 milliseconds. If I change only one parameter, if I change the frame stride, it will be way faster. So that's good, but I have no, at the moment, I have no clue of what will be the accuracy like. I'm just going to set that back to 0.1 because the transfer learning method that we use need to have a fixed length of the frame spline of 0.1. I'm going to save the parameters, and then I'm going to generate the features. So by generating the features, I'm going to go from the raw data to some process features that will be useful to the neural network that can be here and that can be found. I'm going to go back to the generate features. Just waiting a couple of seconds that the neural network, that the pre-processing block works. Running. Usually it takes about like 30 seconds when I've got a small data set like the one I've had. Here I can see, okay, I've got some tinyML words that are a bit mixed in between the unknown and noise. Those 2 ones, I don't really care if they are well separated or not. That's not really a big deal for me. tinyML. Okay, so that's actually a tinyML, but that does not matter. And I've got here an unknown word that is pretty close to the others. Back. Okay. This happens, the quality of the data set. And here the processing time again is 332 milliseconds. Once I've got that, so you saw that there were many parameters that I could change, how to know which one are the best. Then I can navigate to the transfer learning tab or the neural network. Here I've got several hyperparameters that I can fine tune, whether it's the number of epochs, so the number of training cycles, the learning rates, validation set size that I don't really mind. And I can choose different pre-trained model according to what I want to do. I'm just going to leave the default parameters. It will take another couple of seconds, probably minutes at that point. And then I will be provided an accuracy of my model as well as the estimated inference time and the RAM footprint. Here it was pretty fast. So yeah, 30 epochs, that goes fast. We save 2 versions of the model, whether we want the quantized one or the float 32, which is unoptimized, but still it depends on the target that you will need. And I'm going to stop just after that to take a couple of questions. If you have some, feel free to use the Q&A button on the Zoom window. I will take some in a couple of seconds. Okay, so great. Now we've got an accuracy of 95.3%. Actually, the one that I'm interested in is the tinyML word, and this one has only like an accuracy of 85.7, which is good for a demo, but it's not great for a production use case. And the inferencing time will be 336 milliseconds, having a max peak of RAM usage of 45K. And this, we need to sum that with the pre-processing block that is here. So in total, we will need something around 600 milliseconds and I can't remember, so 25 plus 25 plus 45. Okay, so around 70 kilobytes of RAM to make this model work. This is okay. This is acceptable. For this first project, I've been following only the default parameter that Edge Impulse provides. Now, I'm just going to take a couple of questions from. So I've got one from Alexander. What are X and Y axis on the feature map? How to interpret the feature map image? So here the data explorer. So the feature map, I'm not sure if you're speaking about this one or this one, which are basically the same. This is how close your data samples are. We use some embedding techniques on the background. I'm not sure exactly which technique. I think it's TSNE, or you can actually define that in the data acquisition. If you go to the data explorer, you can use some dimensionality reduction technique just to. So there is no real interpretation. The only thing that you need to figure it out is are the data that you are going. Well, do you distinguish some clusters? If so, the neural network will probably learn easily. I hope I answered your question, Alexander. Great. So no other questions from now. So I will go back to the presentation. Slideshow. And yeah, this is just what I've explained. I was not sure I was going to do the live demo at the beginning of when I did that presentation. So here we've got several options that you can define, whether it's which processing block to use, which learning block to use, same which parameters of the, here is the MFE DSP block, but each of the DSP block has some different parameters, the fast Fourier transform length, the low frequency, high frequency, if you want to have add some low pass and high pass filters. And just changing one parameter can change a lot the on-device performances and the accuracy. Same for the hyperparameters here that you want to define. And this is something I've not shown because I've been using the transfer learning, but when you write your own Keras code or use the simple editor that we provide, you have so many options in the neural network parts. You can use, for example, 1D convolutional, which layers to use at which moment, do you need some dropouts, etc., etc. This actually requires some expertise. So we still provide that for people that are actually machine learning aficionados or experts. You can see that those two architectures are, well, they're pretty alike because it's only 1D convolutional, but we have also presets for 2D convolutional architectures. But you can even access the Keras API by switching to the expert mode and write your own code. So this provides the flexibility of the tool, but it's not great for beginners or newcomers. For example, when I started at Edge Impulse, I was not really having any idea of what I was doing when playing with DSP. Digital signal processing was not a thing with me, and I had to learn. But that was really hard. And then came the Eon Tuner. So the Eon Tuner wants to simplify several issues. So the main problem is Model architecture contains many hyperparameters that we have seen, whether it's the windowing, so the window size versus window increase, the DSP, so the number of fast Fourier transform filters, the FFT length, the frame strides, etc., that we've seen. But we have also other kind of DSP parameters, such as spectral analysis when you want to recognize movements. And then in the Keras, the neural network parts, this can be really complex as well. Whether you just want to use dense neural networks or Conv1D, Conv2D, or even some custom blocks. And then picking the right values requires a lot of expertise, either experience, and it's always a back and forth. You test things, you see what's the results, and then you test something else, you see the results, and it can be really tedious and long. And then for some parameters, I don't even know how they function, what will be the impact on the model. That was the case, for example, for the frame stride. Then when we work with embedded machine learning problems, there is one thing that we should not forget is the embedded part. So each of the device is different. Each of the use case is different. For example, for some use cases, the latency will be critical. We want to recognize something as fast as possible. Let's say, for example, I'm in a factory, I'm building a device that recognizes the word help. That's easy to stop the machine, or stop. If this information takes like a couple of seconds to process, then if the accuracy is not great, so you have too many not false positive, well, I'm always confused between false positive and true negatives, but you want to recognize that word always, even if it stops the machine for nothing. And then your model need to fit on the device. So it need to fit the RAM and the ROM, depending on your device constraint. This is some hard constraints that you know. And then the number of possibility can be huge. Here, for example, if you have 4 options for the window size, window increase, 4 options for the fast Fourier transform filters and length, different parameters for whether you want to use some 1D or 2D convolutional, 4 options for the convolutional filters, then you end up with like 1 million possible variants. Well, here only 2048. But yeah, that's super hard. So this is why we developed something called the Eon Tuner. And I want to thank Matthijs on our team. He's the one who initiated and who developed the Eon Tuner. And the goal is to design the optimal machine learning solution within the constraints of your device. So we always have the device in mind. So that's what it looks like. When you start with Eon Tuner, you start by defining one dataset category. So one project that you want to work on. It can be keyword spotting, it can be continuous event, it can be continuous gestures, it can be image classification, object detection, and so on. And then straight after, you define your target device. And we have the list of all the devices that we fully support, as well as some information on just the MCU, such as the Cortex M4, or Cortex M0, Cortex M7, and so on. And last thing, you define the desired time per inference that you want to achieve. For some use case, you can set, for example, 1 second. 1 second is more than enough for you. For other use cases, like the inference time will be critical, as I said. So we want to make the most of limited and heterogeneous computes. We want to find the perfect balance between feature extraction and the model architecture. That's usually hard to calibrate. We provide as well a recommendation based on real performance metrics, so things that we've tested in our lab or with customers. And it's both built for highly constrained devices, as well as some high-end targets, for example, to do some computer vision stuff. And we can provide suggestion on optimal hardware targets for your use case. I'm just going to check if there are a couple of questions, but then you can ask some question and I'll take them in a couple of minutes. So this is what the Eon Tuner actually looks like. I'm going to so let me just check which one is the other. Okay, so I'm going to switch back to the project just to show you what it does look like. So that's the Eon Tuner that I ran before. Here I set my, so when I said, okay, so it's a keyword spotting data set. I can also select something else, but in our case, we want to recognize the word tinyML. I want to run, let's say, on the Arduino Nano 33 BLE Sense, which is variable here. And I want a time per inference around 200 milliseconds. I can go a bit higher, and this does not really matter. I can save that, and then I can start directly the Eon Tuner. That's only a couple of clicks, and then it will run in parallel, like several. I think we run something like between 25 and 50 different combinations, and then we provide the best results. So here, for example, I've got one result which provide me 99% accuracy, and which has like a 100% accuracy in between for the word tinyML, which is actually the thing that I want to recognize. It provides me the window size and the window increase, and all the MFE, so all the DSP parameters, the frame length, the frame stride, and the number of filters. And after, you can get the optimal architecture that has been found. Here, I've been filtering on my validation dataset, but I can also filter on my test dataset. So probably the accuracy will shift a bit. Okay, so that's another model, actually. This one is more likely to be the one I will choose, because it provides 99% accuracy on data that has been unseen to the model during the training. So making sure that the model is accurate. It provides information about the latency, the RAM, and the ROM. So this is great. With only a couple of clicks, you can get things really fast, and you can deploy your model. So the only thing which actually matter in this case is to work on your data. So that's the main thing we tell to our customers and users. Make sure you have quality data sets. Make sure to work on your data set. This will be the success of your project. Okay, so this is about the Eon Tuner, and it's actually great that I'm doing this demonstration today, because last week we also released something called the Search Spaces. So I'm not going to go through the search algorithms. We have different techniques to validate or invalidate the relations between the model that we are using. Yeah, feel free to have a quick look at the search algorithms. Now, we released last week the Eon Tuner Search Space. So it's a bit more complicated, but it still use the power of the Eon Tuner. So you can actually constrain only one step of the Eon Tuner, and then let you define the other parts. And we also release custom block support. So for example, I think I'm going to say an example just in a couple of minutes. So yeah, just a quick context. So for many projects, you will need to use steps that are defined by your hardware. This is what the Eon Tuner is made for, your customer or your expertise. Let's say your project requires to use a grayscale camera because you already purchased the hardware. That's something easy. Sometimes you've got a bunch of camera, it's only grayscale. Before we launched the Eon Tuner Search Space, we were evaluating both RGB and grayscale models. Here you can only define, you say, okay, I only want the grayscale, so one channel image as an input of my DSP block. This is something that you can do with the search space. Another example is your engineers have spent hours working on a dedicated signal processing signal. And it has been proven to work. So you know that that pre-processing actually works pretty well. So there is no need to reinvent the wheel or to test different things. This is, for example, something I've been working with the customers where they want to, using a time-of-flight radar, time-of-flight sensor. We've been working hours on a custom signal processing block, and we know it's working. So there is no need to just to test on different things, and we want to use that. And another example is that simply you have machine learning experts internally or digital signal processing expert in your company, and you have the feeling that a particular neural network will work, and you want only to constrain the search space to look around what you scoped. One example here, I wrote an article a year ago about how to use custom pre-processing blocks in your image machine learning pipelines. So I've been using different computer vision techniques, whether I was using some binary thresholding, some canny filters only to detect the edges of an image. And to do so, just to compare the different things, my main goal was to be able to run the model on the ESP cam, which was a bit tricky at the time to run the MobileNet V2 architectures. So I wanted to just to check if I could simplify the image processing, so I could have a simpler neural network that was a bit more lightweight. So to do so, I first did all the pre-processing things, but after I compared the two results. So I had two projects, and each project I had to define different parameters to make sure well, it was going in the right direction, and I was getting the results that I wanted. I ended up having an inference time of 84 compared to the default one that had of 338 milliseconds. So that was a huge increase of time for me. The max peak usage was a bit slighter. I wanted it to be a bit smaller, but I did not manage to do that. But that had a cost. It was at the cost of the accuracy. So I had a slightly better accuracy. But in my case, that was not a big deal. I wanted to have a model that could work well on that target, because it was the thing that had it was my constraint. So how the search space work? So we use templates to do that. A blank template looks like the following. So you have an input block, a DSP block, and a learn block. So here you've got different things. And we provide different predefined templates that you can use. So you can, for example, load the template for keyword spotting, which actually will let you compare different parameters, audible, even continuous, and that's only for audio, but we have also other templates for vision and for movements. So I recommend having a look at the templates. Usually it's a great way to get started with. So you can modify the parameters, or you can just load a blank template and get started. And then about the search parameters and block. So each element inside an array is a parameter, which means you can stack different combinations. So you can stack, for example, different combination of input, DSP, and learn blocks, like here. But you can also have, I think maybe in learn block, for example, you could have several learn blocks that will use only these inputs. It can be a fixed input and fixed DSP, and you want to compare different learning blocks. And yeah, if you want to go further, you can create an account on edgimpulse.com. I highly recommend that. You can build your first machine learning model in 5 minutes using studio.edgimpulse.com/evaluate. This is a great way to get started. It's actually what I have been using to create the base architecture of the keyword spotting tinyML. And we have all the Eon Tuner documentation on docs.edgimpulse.com/edgimpulsestudio/Eon Tuner. I will just come back to my project just to give you an overview of the search spaces that I just talked about. Okay, so here I've got I think this is the default template for keywords. Zoom a bit so that it will be better for your eyes. So here I've got one input block. It's a time series, so audio data is considered as time series. I've got a window size of 1,000 millisecond and a window increase of 1,000. This is things that you can change. For example, if I want to delete that and use directly blocks, I can use time series, and it will also give me some default parameters. So that's something that you can use to get started. I really thought at the beginning that this was a bit tricky to understand the main concept of the templates, but in the end, it's super powerful, and I'm actually using that a lot because I don't want to train each model independently. I want to test different parameters and different things at the same time. Here for the DSP block, I've got two options. One is the MFCC, and the other is the MFE. And yeah, you can define different frame strength, frame length, etc., etc. And then for the learn block, here it's using Keras. It's using either the DSP1, which is the MFCC, or the second one, which is the MFE. And the dimension that it will use, it can use either convolutional 1D or convolutional 2D. I've got some base filters that I can already define. I've got some convolutional layers that I can define, but you can also delete that and add a block. And for example, if you want to say I only want convolutional 1D, okay, so that's easy. You can just select that. And then I've got something completely different that will be tested in parallel, which is the Keras transfer learning. So our own transfer learning technique for keyword spotting, and you can use two different model variants, whether you use a MobileNet V1 or MobileNet V2. And here we have a fixed learning rate and a fixed training cycle, but you could also define another learning rate. So, for example, if you have a doubt, you can set the two parameters, and it will run that in parallel. I will take a couple of questions. So that's it for me. It's 40. So we have another 5 minutes of presentation. I think I've been a bit quick. So yeah, I will have more than enough time to answer all your questions. And so again, Alexander, 1024 kilobyte for the ROM is the final required size, or 100 kilobytes. This is the full available capacity. No, what we provide is the size of the model. So you will need to know what's the maximum size for your device. Yeah, that's the size of the model. I hope I answered your question, Alexander. You've got another question. Classification algorithms are always inherited from base model, or is it possible to alter it with Eon? I'm not sure I understood your question. Maybe this can help as well. When you load a template, you can also load the exact template that you created when you designed your impulse. So let me do that here. And so it will basically take all my parameters, and then let's say you want to test different things on the, let's say you just want to test different learning rates. You can do this, and here it will test in parallel two different learning rates. I'm not really sure I answered your question. Feel free to tell me if not. No other questions? Maybe in the chat. No. So we have the chat and the questions open. Well, while you're writing your questions, I will also be here, be there next week in the tinyML Innovation Forum in Cyprus. So if some of you are going to be there, I would be more than happy to say hi and to explain more in details if you need some of the things about the Eon Tuner or anything else about Edge Impulse. I will be actually giving 2 talks over there. One will be a tutorial on how to build a people counter that will use a camera device. So we'll be doing object detection on MCU. And the second talk I will be giving will be on the deep dive, what's behind FOMO. So it's one of our techniques, which stands for faster objects, more objects. So it's an object detection technique, and I will be giving like a deep dive session into this.
Well, thank you very much, Louis. I don't think we've got any more questions at the moment. Is there any last questions?
Alexander, thank you again, Alexander. Yeah, got a lot of questions. I love that. When training models for sensor data like accelerates, what machine learning techniques are possible? So I would recommend to use some spectral analysis DSP block, so DSP preprocessing. So what actually the spectral analysis does is we detect peaks of frequencies, detect different things from the signal, and from that we extract some meaningful features, and then you can use some really easy neural network, so maybe 2 or 3 layers of dense layers, and as a result, I've been noticing that this actually works pretty well. I gave a workshop about 6 months ago, maybe, on how to recognize different kind of movements. It was to recognize jumping jacks, squats, and rest, and a couple of movements using only accelerometer, and the accuracy is pretty impressive. Only with a couple of data, a nice preprocessing block, and like 3 layers or 2 layers of dense neural network, it's working great. And do you have support for RNN or plans to implement it? No, not yet, or I'm not even sure I can say yet. We could support that because we have something which is actually pretty new, that is called bring your own model. So you can bring your own model onto Edge Impulse. The only thing is, I'm pretty sure it won't work as expected on microcontroller. Sorry, on macrocontrollers. So you could use edge devices such as the Raspberry or Jetson Nanos, but that's a bit outside the scope of MCUs. And one of the reasons, I think, it's because TensorFlow Lite Micro does not support RNN at the moment, and we rely on that for compiling our model on microcontrollers.
Okay, it looks like we've... Oh, no, there's another one. Oh, okay. Thank you.
Thank you, Alexander, for your questions.
Yeah. Okay, well, thank you very much, Louis. Do our normal end off, thanking all of our tinyML strategic partners, the executive strategic partners, Arm, Edge Impulse, Qualcomm, Sentient, and the platinum strategic partners, Deep Light, Clickertech, Reality AI, Renesas, Sony, and the gold analog devices, PhotoHub, Microsoft, NXP, Seed, SenseML, ST, Synaptics, SynSense, and all our still strategic partners. And thank you also for attending the talk. Thank you.
Yeah, thank you, everyone, and thanks again, Martin and Rosina, for hosting this webinar. I was really happy to be here today.